Hello everyone. Can someone please confirm if they can see the screen?
Yes, sir.
Okay, Karthik. Thanks. So let's begin our discussion from where we left off in the previous discussion hours. So currently what we are studying in the lectures is manipulator kinematics, right? And just to recapitulate what we have done in the previous weeks, so especially in the last second week, so the major concepts were the forward kinematics and inverse kinematics, and prior to that we have seen frames, how to assign frames, how to write transformation matrices, right? And the DH convention for the same purpose, assigning frames and writing transformation matrices, convenient ways to follow the DH convention. So any questions in these topics? If there are, then you can please go ahead. Okay, so let's start the today's content. So in so last week we covered till inverse kinematics and we solved a few questions around that. We saw that inverse kinematics can be done analytically and also numerically, right? So if you would have seen the recording of the session, I mentioned the two approaches, analytical and numerical. So analytical has a closed form expression. Basically, you have well defined expression for the theta 1, theta 2, and whatever so on. And in numerical, you solve for the joint angles either iteratively or using like matrix inversions. So in week three's assignments, there were two questions which were based on this concepts. All right. So for any manipulator or robotic system, or in fact for any uh, multi-body system, multi-body rigid body system, we have relation between the task space, which is usually denoted by x, right, and joint space, or another term is configuration space, also called as C space, right? So task space is where we specify the tasks. We give Cartesian trajectories for the end effectors. Let's say we want to move in 2D plane from point 1 comma 2 to 5 comma 10, and at equal intervals we specify these xy positions, right, to form a trajectory. So this is the task space description, and from here, using inverse kinematics, we go to a sequence of theta 1 and theta 2, right? So basically for each of these points, if you do inverse kinematics, get the theta 1, theta 2, so you will get the trajectory of the joint angles, and that is the quantity which is commanded to the manipulator, right? So your manipulator having motors at the joints take into this joint angles and drive to that position. So what you would see in the end is that end effector would attempt to follow, not precisely follow, because therein lies in the aspect of tracking and control, which we'll see going ahead. So basically the aim is that the end effector follows the desired trajectory, right? So till now we were dealing with positions and joint angles, right? We were going back and forth between positions and joint angles. Now what we will see is how are the velocity I should write the end effector velocity or linear velocity, how do they relate to joint rates, that is the rate of change of joint angles, right? So that's the another step which we want to take, is relating these two quantities. So usually the relation between the task space and the joint space we can write as, right, this is the task space vector, this is the joint space vector. Now to find a relation between the velocities, the first step is to basically formulate a mathematical relation that if we do a small change in theta values, then what is the small change in the end effector value, right? Because velocity is in turn what? Velocity is change per unit time, right? That is velocity or rate, change per unit time. So we want to relate the change in the joint angles to the change in the position of the end effector, or for that matter any specific point on the manipulator, right? So how are these two related, right? So if from general maths, if we have, let's say, y is a function of x, right? Then if we want to relate how much y changes if I do a small change in x, then what do we do, right? We do this, right? Del y by del x, basically, which is del f in this case by del x, right? So del f by del x, what does it give? That what is the rate of change, what is the rate of change of y with respect to x? So a small change in y relates to a small change in x via this relation, right? So this is a, you should be very careful with the symbols. You should see that I'm using a, this kind of a symbol. This is to denote a small change, infinitesimal change, very small change. So this delta of any quantity is a small change in n quantity, and this del by del x, right? And this thing is an operator, right? It's like an operation that which you are doing on that function. So this is the derivative, or more precisely the partial derivative operator. So if you are not clear at any point, just raise a question. So partial derivative operator. So there is distinction between these two symbols. I'm not using them arbitrarily. So a small change in x relates to a small change in y through this quantity, right? So that's the quantity of interest which we will find. So similarly in this case also, a small change in end effector position relates to a small change in joint angles via this quantity, right? This quantity.
Sir,
Yeah,
sir,
yeah, go on.
uh, can you repeat this part, sir? I didn't understand properly. Like in the second step, you wrote dy by that is dou y by dou x. You have
Yeah,
written, no,
yeah,
sir.
yeah,
Then from that step, that one we just took the partial derivative, no,
yeah.
sir, over there.
Yeah, yeah, right, right.
After that step, what did you wrote, sir? That is del y. You told us very small. I didn't. I'm not able to link those two things, sir. Can you explain that part, sir?
Yeah, sure. So this I was giving a general example, right? That we can find the rate of how much y changes if I change the x. If I change x, let's say y and x are related by the function this is which is fx, right? So if I change x by little bit, then how much y changes, this is found by partial derivative of f with respect to x. All right. So again, the next step which I wrote here is basically using that relation to find that small change in y, right? So multiplying a small change in x with this quantity gives me the small change in y, right? It's basically, this would be, in some case, let's say a matrix. This would be, this would become much clear if I give you an example which I'm coming on to. So, and this will again be a vector. So let me just take an example here. So let's say y is equal to x square, right? This is the relation. Here f of x is x square. Okay. Then if I, then what I want to know is if I change from x to x plus delta x, right? This delta x is a small change. Then where does y go, right? That's the thing we are interested in. So one way is to, do it manually. So let's do that, right? So the new y, let's say y dash, is x plus delta x. By the way, is my handwriting visible to all, or should I write in bigger font?
It's visible, sir.
Okay. So y dash is this new x, which is x plus delta x. So let's take the square, x square plus x 2 times, so usual a plus b, the whole square formula. This is 2 and delta x square, right? So now, this quantity, this expression, this has a term delta x square. So what we will do is that we will ignore that term because that's the square of a very small quantity. So that's even smaller compared to the other two terms, right? It's like, let's say x is equal to 5 and delta x is, 0.001. So the square of that quantity is also very small. So we'll ignore that quantity. So the remaining is, so rather than using a equal to sign, I will use approximated as x square plus 2x delta x, right? Now this is the new y. So now this expression, what this is equal to is, so y dash is, now x square, initially what we wrote, x square is equal to y, right? So y dash is equal to y plus 2x into delta x, right? Now let's take y to the left hand side. So y dash minus y is equal to 2x into delta x. Now y dash minus y is what? The change in y, right? And we do not change in y by delta y. So delta y is 2x times delta x. And here is that relation which I was mentioning, that the change in small change in x is related to small change in y by some quantity. And in fact, if you would have done directly, like originally y was x square, so if you have done del y by del x, right, which is what, 2x, right? So this quantity is nothing but del y by del x. So that's how this partial derivative or derivative of that function relating y and x comes into the picture, right? So is it clear now?
Yes, sir. It is clear, sir. Yes.
Yeah. So similarly, so this was a very, simplistic example. You would have more complicated functions, or as you will see in this case, we will have functions which are basically vector valued functions. Like they take not a single value as input, but a vector of values as inputs. Because there will be more than one joint angles in almost all cases. So coming back onto the manipulators. So the joint angles, a small change in joint angles is related to a small change in the end effector position by this quantity. And this quantity is frequently used in robotics and is given a special name which you will encounter very frequently from now on, which is called as the Jacobian, right? So Jacobian is del f by del I wait, small mistake here, just I mixed up notations. So here there will not be x, there will be theta, because that's the independent variable. Like you derivate it with the variable on the right hand side, so it will be theta. So del f by del theta. I am putting this bar below to note that these are all vectors and vector valued functions. Okay, so let's first of all very quickly, let me make some space here. Okay, so let's take an example on our most common and useful system, 2R manipulator. So Jacobian of the end effector for a 2R manipulator. One thing we should note is that Jacobian can be found not only for the end effector position. We usually find it for the end effector because that's a point of interest, because that's the part which we are concerned that it should follow a trajectory or should reach at a certain point. But Jacobian can be found for any point on the manipulator. Let's say I want to find the Jacobian of the first, where the two links join, the middle joint. I can find Jacobian for that point also, right? So Jacobian just relates the change in joint angles to a change in the position or the task space of any point. Okay, so let's draw our usual 2R manipulator. So now you'll be quite comfortable with these symbols and notations because they are repeating from the first week itself. So L1 and L2 are the link lengths, theta 1 theta 2 are the joint angles. This is the x direction, this is the y direction of the inertial frame or the base frame. Okay, and this is the end effector. So let's denote the end effector position as small x comma small y. So 2 are planar manipulator. So the end effector position vector is x y. Okay, this is the task space quantity, and the joint angle vector is, this is capital theta, so that is theta 1 and theta 2. Okay, so we have also seen what is the relation between the position of the end effector, basically the expression of the position of end effector in terms of L1 L2 and theta 1 theta 2. So I will write it directly now. So x is L1, and this notation also is familiar, that C1 is cos theta 1, S1 is sin theta 1, right? C12 is cos of theta 1 plus theta 2 and so on. So L1 C1 plus L2 cos theta 1 plus theta 2. Similarly, y is L1 S1 plus L2 S12, right? So this we know. Now let's write the same thing in expanded form, because I would like you to see how we are taking the derivatives. Okay, so and let's write them in the vector and matrix form. So xy, this end effector position vector, is xy, and xy is L1 cos of theta 1 plus L2 cos of theta 1 plus theta 2, and L1 sin theta 1 plus L2 sin theta 1 plus theta 2. Okay, so now just take a moment and take the derivative of this vector with respect to theta 1 plus theta 2. Okay, so are you guys comfortable with taking a derivative of a vector with respect to a vector, or have you done this derivation before? Can anyone let me know? Because accordingly I will spend time on this. Okay, so let's do it thoroughly, right? So this is a 2 cross 1 vector, right? Now in this case, right, which you saw here, what we have is a function scalar function, and we are deriving it with respect to a scalar quantity x, right? Now let's take another example. uh, let me write a vector. Okay, so let me write v is equal to 3x square plus 4y and x minus y cube, let's say. Okay, so this is a vector which is dependent on x, which is also a vector containing x and y. Okay, so what we have to find out is derivative of the vector v, which is a function of x with respect to vector x, right? So how we proceed is, so let's say this is v1, this is v2, okay? So the first is, so now each of these expressions, the first element of v and the second element of v, these are scalar expressions, right? So this is a scalar expression, a function of x and y, and the second element is also a scalar expression, a function of x and y, okay? Now what we do is that we first derivate v1 with respect to x. Then, so basically we take the first element of the vector v and derive it with all the elements one by one of vector x. So del v1 by del x, del v1 by del y. Similarly, del v2 by del x, del v2 by del y, okay? And since this is a 2 cross 2, so what you see is that derivative of a vector quantity with respect to a vector quantity is a, it's not a vector but it's a matrix, right? This is a matrix. So point to note is that derivative of a vector quantity with respect to a vector quantity is a matrix, right? So, and if there would have been, let's say, let's say there would have been another variable z, so there would be one more column here, right? So you can also tell by the number of elements in v to the number of elements in x, like what will be the size of the resulting matrix, right? So since there are two elements in v and two elements in x, so this is a 2 cross 2 matrix, and that's the case here too, right? We have two elements in x and we have two elements in theta, which is theta 1 and theta 2. So again, the first element is a scalar expression in terms of theta 1 and theta 2, and similarly the second expression. So what we will do, we will follow the same thing which I showed here. First element, derivative with respect to x, which is theta 1, derivative with respect to theta 2, then the second element, and again derivative with respect to theta 1, derivative with respect to theta 2, okay? So let me write this here explicitly. So delta x, which is a function of theta with respect to, no, again I am used to writing x at the bottom. So theta, right? So the first term, let's derive it with respect to theta 1. So it will be L1 S1, right? Derivative of cos theta 1 sin theta 1 minus, and the second term also has theta 1, right? So minus L2 sine, and derivative of cos theta 1 plus theta 2 is, with respect to theta 1, is sine theta 1 plus theta 2, right? So S12, okay? This is the first row, first element. Now first row, second element, which is derivative of the this first element of x with respect to theta 2, right? So I would suggest you should also follow along with me for better understanding. So derivative with respect to theta 2 is just in the second term, so it will be minus L2 S12, right? Similarly, the second element we can write L1 C1 plus L2 C12. This is the second row first element, and the second row second element is L2 C12. This is a 2 cross 2 matrix. Any questions in the derivation part? Taking derivatives, any doubts in there? Just take a moment to do it on your own.
Sir,
Mm-hmm.
I don't have doubt in the derivation, sir. Here, x and y, they are scalar, no, sir?
Mm-hmm. Yeah.
And L1 cos theta 1 plus L2 cos theta 1 plus 2, those are also scalar.
Yeah, yeah, yeah.
Here, why are we taking the dou x x of theta and divided by dou theta we have written, no, sir, here.
Mm-hmm. Yeah, so
That one, in this case, x is acting like as a vector, no, sir.
yeah,
And
so just I
like
think you, so this is the capital X, right? Which is the vector containing small x and small y, right? So capital X is a vector, the end effector position vector, right? And
okay,
which has two scalar elements x and y, small x and small y. Capital theta, again similarly, capital theta, which I have written here, capital theta is the 2 cross 1 vector whose elements are theta 1 and theta 2, which are scalars, right? So I could have written this as like this also, that capital X and a function of theta 1 and theta 2, right? This is same as writing, since I have defined a vector for theta 1 and theta 2 also, so this is same as writing vector x and it is a function of vector theta, right? So yeah, just for writing it more compactly again, so that's the notation used here. So we are taking the derivative of capital X with respect to capital theta. So we are taking derivative of capital X vector with respect to capital theta vector. Okay, and then again followed the process here.
yes, sir.
Okay, so now this matrix which we got, here is the Jacobian of the point P, which is the end effector, right? That is, to make some space here, these are few questions which I will discuss later. Okay, so let's continue here. I will put a remark here. Some of these word messes it up. Okay, so continued. So let's continue here. Okay, so the J matrix, let's rewrite it here once again, is minus L1 S1 minus L2 S12, second element L2 S12 minus then L1 C1 plus L2 C12 and L2 C12. Okay, so this is the Jacobian. Now what next we can achieve from here is that what I mentioned here, that a small change in theta is related using Jacobian to a small change in x, right? So a small change in end effector position, that is del x del y, okay, is equal to j times a small change in the theta or the joint angles. So j into del theta 1 del theta 2, right? So this is a small change, and if we divide both these vectors by delta t, right, which we can do, let's say a small change occurs in a delta t time, right? Is equal to j times delta theta 1 del t delta theta 2 divided by del t, right? So now what these quantities have become is, this is x dot, right? This is because this first thing is x dot, this is y dot, and this has become theta dot. Okay, so what's the relation we have? That the end effector velocity in the Cartesian space or the task space is related to the joint velocities or the joint angle rates through the Jacobian matrix. And this is the first very useful relation which we use day in and day out in robotics while doing kinematics, right? And similarly, if j is invertible, you will see cases when what happens when j is not invertible or j is not non-square. So j is not necessarily square, right? It is no mandatory that j should be a square matrix. J can be a rectangular matrix, and in fact most of the cases it is a rectangular matrix, so especially for redundant manipulators. So the reverse thing is that if we want to know the joint angle rates given that we have the end effector velocity, then we can do this, right? So like, try to get the uh, consequences of this result that we have just derived, that for a given manipulator, right, the end effector, let's say we are just concerned about end effector. So for the end effector you can get the Jacobian matrix, you can derive it once analytically, and you can program it in a, let's say whatever the program you're writing for the manipulator, you have to just do it once. Once the Jacobian matrix is with you, the closed form expression of the Jacobian matrix, you have to just evaluate it at the joint angles, whatever configuration the manipulator is at currently, and you will directly get from the end effector velocities from joint rates. So let's say this is just a 2 hour manipulator. Let's say you have a 3 hour or 6 degree of freedom manipulator, complex, or not even manipulators, complex other robotic systems. Let's say a wheeled robot with a manipulator on top, whatever be the complexity of system. Once you have the Jacobian of the matrix, you need not do the kinematics of the system, link by link, which is prone to mistake and difficult to program also. So you can just directly get a mapping from this space to that space, from joint space to task space, and you can keep switching between uh, these two by using either Jacobian or the inverse of the Jacobian. So that's the beauty of it. So, and I should, for completeness sake, I should write that J is not a constant matrix. J is a function of theta. J is still a function of theta, right? Because this is, in fact, there are sine and cosines of theta 1, theta 2 here, right? Which, so at different configurations, the Jacobian matrix will change. So it's not that the Jacobian of the end effector is always the same. It depends on the configuration of the manipulator. Okay, so let's spend some time on this expression now. So what we have is that the joint rates is given by inverse of the Jacobian. Now, for a typical square matrix, the inverse of a matrix is adjoint of that matrix by the determinant, right? This you would be familiar with. So now what you see is that the quantity appearing in the denominator is determinant of J, right? So whenever some quantity appears in the denominator, we definitely ask another question, right? What if this quantity becomes 0, right? Because division by 0 always creates some problems, right? So, and always gives rise to some interesting insights. So what happens when det J is 0? Then what happens, right? Okay, so first of all, when det J will be 0 or determinant of J will be 0, then basically the right hand side will tend to infinity, or theta, in other words, theta dot will shoot up to infinity. Theta dot will tend to infinity, right? So, and if a matrix determinant is 0, then what do we call it? That J is singular. Okay, a square matrix whose determinant is 0, we call it as a singular matrix. Okay, and singular matrix force us to handle them very carefully. So we need to avoid. So basically, let's say you are trying to, you have programmed something, you are giving joint rates, you are getting velocities of the end effector, and then suddenly you're at some theta 1, theta 2, your determinant of J becomes 0, and your joint velocities blow up. They go to infinite, and infinite means that in actual, like in a computer program, it would return a very large number, and if that velocity is commanded to the motors, a very large velocity will suddenly go to the motors, and the hardware might get damaged, right? So from a practical point of view, these are the values which we need to find out, and we need to avoid them. We need to make sure that the manipulator does not go into that position, or as soon as it approaches that position, it should be aware and try to avoid that position. So let's analyze for 2R manipulator, like what are those positions where this happens, right? So what we will do now is singularity analysis. For a 2R manipulator. Any questions till now? Okay. So first of all, what we concluded is that singularities happen when determinant of the Jacobian is 0. Okay. So let's find out the determinant of the Jacobian in our case. Again, I am writing the Jacobian for reference. It was L1 S1 minus L2 S12 minus L2 S12 L1 C1 plus L2 C12 and L2 C12, right? Now what is determinant of this matrix? So again, determinant of a 2 cross 2 matrix which elements are, let's say, A, B, C, D. So the determinant is AD minus BC. Okay, so determinant of J is, let's multiply. So L1 S1 minus L2 S12 into L2 C12 minus, so minus, and there is a minus here also, so it will become plus L2 S12 into L1 C1 plus L2 C12. Okay, now let's open these brackets carefully. So first term L1 L2 S1 C12. Again, please do it along on your notebooks also, so that if I make a mistake also you can point out, and otherwise you will also get a clearer understanding. So L2 square S12 C12, right, plus L2 L1 S12 C1 plus L2 square S12 C12. So this term gets cancelled straight away, right? What we have is L1 L2 times S12 C1 minus S12 C12. Okay, now again using our trigonometric identities, this is sine A cos B minus cos A sin B, right? So this is sine of, here let's say A is theta 1 plus theta 2, B is theta 1, so sine A minus B is theta 2, sine of theta 2, and L1 L2. Oh, I missed these messages. Yeah, step size will play a major role in smoothness of joint angle. I mean, in practical application, you would choose what level of discretization you will have to your trajectory. So that depends on other factors also, like how fast your motors can receive and execute commands. So again, that's a whole aspect of it, like practical implementation. So if we have time at the end, we can discuss it, but let's get back to this here. So finally we have determinant of J is L1 L2, which are constants, and sine of theta 2. Okay, so it has a dependence on only the second joint angle, not the first joint angle. Interesting. So when will this be 0? So L1 L2 sine theta 2 is 0, implies that sine theta 2 is 0, implies that theta 2 is equal to either 0 degree or 180 degree, right? Or similar. I mean, a general solution could be plus minus n pi, right? That's the general solution for sine theta is equal to 0. Okay, so let's sketch. Since we are working with 2R manipulators, we can easily sketch these configurations. So let's sketch these configurations to get a clear picture of what are these positions of the manipulator. Okay, so let's do the first case when theta 2 is equal to 0. So in this case, our manipulator, so since there is no restriction on theta 1, we can put it at an arbitrary angle, and the second link is like this. Okay, so this is theta 1, and the second link is perfectly aligned with theta, sorry, the first link. So theta 2 is 0, right? So what is this configuration? It is a fully extended, right? So in this case, if this is L1, this is L2, so the end effector is at a point L1 plus L2, the distance from the origin. And what we have seen earlier is that in fact this is the radius, the outer radius of the workspace, right? So basically what we have is that our end effector is at the limit of the workspace, right? So this is what we called as a boundary singularity. So now any of these points on this boundary, because theta 1 can be arbitrary, theta 1 you can rotate from whatever joint limits that you specify, and for theta 2 is equal to 0, the end effector will always be at the edge of the workspace, so it can't go further, right? So that's basically you are losing 1 degree of freedom. So the practical implication is that you can't go further in the extend your arm any further. So you can just move, if I draw an axis here, if I draw axis here, which is, let's say, y dash and x dash. So you can't go in x dash direction, you can only move your end effector in y dash direction. So effectively you are losing 1 degree of freedom. Your manipulator is a 2 degree of freedom mechanism, but at the singularity point you lose 1 degree of freedom, right? So that's the consequence. And in general terminology, we say that the arm or the manipulator has locked out, right? It can't extend any further. So that's the first case when theta 2 is equal to 0. The second case is when theta 2 is 180 degrees. Now in this case, as you would guess, what will happen is that, so now this is the theta 1 and theta 2 is 180, so directly here, right, 180 degrees. So basically the link 2 is on top of, folded back on top of, link 1. So the end effector is here if link 2 is smaller than link 1. So in that case, there is again what we have seen before, is that annulus, right? So if link 2 is smaller than link 1, then there was this annulus, right? This was the reachable workspace, and here was the center. So these points can't be reached, right? And this boundary is where theta 2 is 180 degrees, right? So that's the, again, the inner boundary of the workspace for this manipulator. And similarly, there also you lose 1 degree of freedom. You can't move in the normal to the this circular curve. You can just move in tangential direction to the circular curve there. Okay, so guessing, you would see that for any manipulator, then, since the boundaries of the workspace are related to the singularity locations, so you can, earlier we derived, or earlier we drew the workspace just by intuition, right? That where it can reach, it can be fully extended or fully folded. But you can also draw these workspaces by doing singularity analysis, right? You can see that theta 1 can be arbitrary. So, and if there are no joint limits, then theta 1 can go all around 360 degree, and theta 2 will have a limit, will at 0. So at 0 degree you will have a limit, and at 180 degree you will have a limit, like it can't go any further than that. So you can draw workspace like that also. Okay, so what we saw is that to our manipulator has boundary singularity at theta 2 is equal to 0 degree and 180 degree, right? In practical applications, what we would do is that we would avoid giving such positions of the end effector which correspond to these angles, right? Basically, we would keep all our trajectories well inside the workspace, not go close to the uh, edge of the workspace, because as you would see, I guess you would have seen in the manipulability lectures, which will be discussed ahead, is that as you go closer to the edge of the workspace, the manipulability ellipsoid gets very flattened and in the end becomes a straight line. So you lose manipulation ability. And as I mentioned, the velocities would rise very rapidly. So again, the arms would get locked out, and basically some bad things can happen there at those points. So for practical implementation, you would like to do this analysis first and keep your trajectories well inside the workspace. Okay. Now, so one thing we saw is the existence of the singularity points. Now, the other thing that we can see from the expression of,
Sir,
yeah, go on.
sir, can you just scroll little up, sir?
Mm-hmm.
Uh, Here, sir, for the fully extended configuration,
Mm-hmm.
we discussed that since the configuration in the fully since the configuration of this manipulator is in fully extended mode, it loses the degrees of freedom we discussed, no, sir.
Mm-hmm.
Like uh, by that you mean theta 1 is independent. That's why we are telling because theta 1 has no effect on on Jacobian.
Determinant.
Uh, is that why you said it has lost degrees of freedom?
No, not exactly. So let me put it once again. So let's say you are at this position, right? Fully extended position. Okay. Now the goal, so what we, when you say that you have a 2R manipulator and you are working in a 2D plane, so you say that you can reach any point x comma y, right? But once you reach at the edge of the workspace, right, let me draw it once again. So this is a workspace, and let's say there is one configuration like this in which it is not at the edge, no. So here in this configuration, basically if I draw a frame here, you know, let me choose another color. A frame, one is along the link and other is perpendicular to the link, right? So if I draw a frame like this, then from this configuration I can move in both these directions, right? As you can imagine, I can go slightly ahead, and I'm not talking large changes, also like slightly ahead in this x dash direction also, and slightly in y dash directions also, right? I can change my angles like that, theta 1 and theta 2, such that if I am here, I can go either here again. Let me choose one more. So I can move along both the directions. I can go slightly here also and here also, right? And these are two independent directions. They are orthogonal, right? So I still have the full degrees of freedom of the system, which is 2 in this case, right? Now when I am at the edge of the workspace, you know, my arm is in fully extended configuration, so the end effector is here, right? Now again, if you draw the directions there, one along the link and one perpendicular to the link, then from physical intuition also you can very well say that in the x dash direction you can't move any further, right? You can just move slightly in this. You in y dash direction you are free to move. In this fully extended, it's basically like a locked out rod moving in a circular path, right? So y dash direction you can go from this point to this point, but this point, this, let's say this is a p dash point, this is out of your reach, right? So effectively, and for as long as you keep theta 2 is equal to 0, right, you can only, from this position you can only move in direction perpendicular to the link 2, right? You can move only 2 points in these directions. You would have to change your theta 2, you would have to change your theta 2 to some other angle in order to regain ability to move in this direction, you know. So we'd have to bring it in some other way to bring it down. You can't just go to p dash. So at this position, I'm not talking about other positions, at this very specific position when theta 2 is 0, you can only move in one direction, right? P dash point is not reachable. And so since this is again a 2D plane itself and one of the directions is not accessible to you, so that's why I said that the manipulator has lost 1 degree of freedom.
Yes, sir. Okay, sir. Clear, sir.
Okay, cool. Okay, so theta dot was J inverse the task space velocities, and for square matrices this was adjoint of J by determinant of J and x dot. So first we saw that J is 0 at singularities. Now when will be theta dot maximum? Theta dot maximum, because that, or in fact not maximum, pardon me, when it is maximum is like taking it to infinity, so which is the case we just saw. When will theta dot be minimum? And minimum because theta dot is directly related to energy, right? Kinetic energy. So when will the energy be minimum? And when it will be minimized? When determinant of J is maximum, right? So the next thing which you have to find is for what theta 1, theta 2, or what configuration det J is maximum. Because that is the most energy efficient configuration of the manipulator. So the configuration in which, in order to move, it takes the least amount of energy, right? So det J was L1, L2, theta 1, theta 2, right? No, sorry, sine theta 2. L1, L2, sine theta 2. So this is maximum when theta 2 is equal to 90 degree, and here we are considered about the mod of determinant, like either, so it will be the maximum of sine is plus minus 1, so this is plus minus L1 L2, right? So theta is equal to 90 or 270, and so on. So let's draw this type of a configuration. So this corresponds to, again, theta 1 can be arbitrary and theta 2 is perpendicular to theta 1, right? This configuration. So this is L2, this is L1. So basically this is the configuration in which the 2R manipulator is in most energy advantageous position, right? So again, this is also a good thing to know, and we'll also see ahead that how our when we talk about dynamics, we will see how torques and end effector forces are related again through Jacobian itself, and then again we will see what's the significance of this configuration. So just keep in mind this point also. Okay, so so I would stop with the theoretical discussion at this point for today's discussion, and I will go on to solve a few questions, right? So first question which I had selected, it's here, let me bring it down. Hmm. Okay. So let's. So this is again. This is question from concepts based on week one, week two, right? So just to again revise a few things because we need to keep on solving such kind of questions until we are quite thorough with them. So this is a 3R manipulator, but this is a 3R non-planar arm. Earlier we have seen 3R manipulator in which all the three revolute joints have parallel axis of rotation, but in this case the axis of rotation of the first joint is not parallel to the other two ones. So basically this is in this direction, so in the plane of the paper, and the z of these two, they are outside the plane of the paper. So this is z1, and I would say z0 is also there, so z1, this is z2, and this is z3, right? So as you would imagine that when theta 1 changes, this manipulator will move out of the plane of the paper, right, as theta 1 changes. So it has the ability of moving out of the plane of the paper also. And yeah, the other two links, if I fix theta 1, the other two links is just a typical 2R manipulator thing, you know. So it's like a, so the part till here is a 2R manipulator, and basically a 2R manipulator is attached to another revolute joint which can take that 2R manipulator out of the plane also. So that's the insight here, and basically we have to write the DH parameters and form the transformation matrices. Okay, so let's write the DH parameters. Link twist, link length, joint displacement, joint angle. So again, please attempt the question parallelly on your own also. This is not a very complicated question. Oh. Hmm. So the z-axis I already drew. The x-axis can be drawn along the links. So this is x01, this is x2, and this is x3. And
Sir,
yeah.
over here, sir, you have drawn you have marked x3, no sir, x3 axis.
Mm-hmm.
I know the DH parameters, and I have solved few questions, sir.
Mm-hmm.
I don't have doubt regarding the concept. This is just I had this confusion, sir. Like we take x-axis, like x-axis is taken between two consecutive z-axis, no sir. Shortest distance between two consecutive z-axis, no sir.
Mm-hmm. Mm-hmm.
X-axis. That's how we assign x-axis according to DH parameters, no sir.
Mm-hmm. Mm-hmm.
When we apply the same thing here, sir, x3, sir,
Mm-hmm.
there is no z4, no, sir, here. So
Mm-hmm.
for the extreme end, last end, there will be only one axis, no, sir. That is z. I
Mm-hmm.
mean,
Mm-hmm.
only one frame will be available, no,
Yeah,
sir.
yeah, yeah.
So
I get you.
because we have followed a pattern of assigning x1, x0, x2 along the links, that's why we directly seeing that pattern, we mark the x3 is equal to along that end effector.
Yeah, yeah.
Seeing just by seeing the pattern, we mark, no, sir.
Yeah, right, right, right,
For
right.
the last one. For
Yeah,
the
yeah,
last one.
yeah. And you know, and for if you again, if you want to follow it quite rigorously, so you can mark a frame here also. Like no one is stopping you from marking a frame here, which is just a frame which is translated from this third frame. A translated frame, you can mark a fourth frame here also. So again, but there would also be a x4 there also, which you will point out just along x3. So
Uh,
yeah, I mean the point that you mentioned is that it's a common normal between z2 and two consecutive z axis. That's also correct, and usually they lie along the link lengths also. So and this for these manipulators, you are just conditioned by solving such problems is that you directly mark them along the link lengths without thinking much. Again, every time without thinking much about where is the other frame to which this x3 is pointing to. So yeah, it's fine.
so by seeing the pattern only we mark, no sir, this one.
Yes, yes, yes.
Seeing the pattern of previous x axis,
Yeah, yeah,
we
yes.
directly.
Yeah.
Okay, 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 sir.
So link twist. So first link twist is 0 because z0 and z1 are coincident. Length is 0. This is 0. And this is the angle between x0 and x1. So this will be theta 1. Now here is where the change will come from the planar case. So now z0, sorry, z1 and z2 are not parallel, but they are at an angle. And rotating about the x1 axis, we rotate by plus 90 to get to z2, right? So this is the link twist between z1 and z2, which is of plus 90 degree. The link length is L1. There is no prismatic joint, and this is theta 2. Now again z2 and z3 are parallel, so this is back to 0. The distance between them is L2. There is no prismatic joint, and x2 and x3 is theta 3 angle from x2. So this completes the TH table very quickly. So once you have this, let's write the transformation matrices. So we have 4 frames. We have 0 to 1, then 1 to 2, then 2 to 3. So 3 transformations. We have 4 frames, 0, 1, 2, 3. We have 3 transformations. So let's write t 0 1 is equal to. Now I would, again, you can recall the huge formulae and write using that, but since this is a quite simple case, so you can again write from your understanding also. So first part will be the rotation matrix from 0 to 1, which is there is just a rotation about the z axis. So and theta 1 is the angle, so this will be cos theta 1 minus sin theta 1, sin theta 1, cos theta 1, 0, 0, 0, 0, 1. This is that rotation matrix part. This is the usual part, and finally this part is the location of the origin, right? So since origin of 0 and 1 are coincident, so this is all zeros. So this is t 1 to 0, and then let's write 2 to 1. So what's different in 2 to 1 is that there is a rotation about z by 90 and x about uh, theta 2, right? So this, for this, writing is slightly more involved. I will write it directly here, but you can. So first let's write the translation part. The origin of second frame, which lies here. The origin of second frame from the first frame is at a distance of L1 along the x1 axis. So That is straight enough. Okay, and then what we have basically is a rotation about the of about of 90 degree about the x-axis, and a rotation of theta 2 about the z-axis, right? So this is so let's write it as what is this, z theta 2 r x, this is z 2, okay, this is x1 by 90 degree. So rotation about z is c2 minus s2 s2 c2 0 0 1 0 0, and this is about x, so 1 0 0, this is fixed, then c cos 0 sin 90 minus sin theta and 0. Okay, so if we multiply these two, what we get is I think this would be oops. A lot of things got deleted. Good. Okay. So let me write again. Zero minus one 0 c2 minus s2 s2 c2 0 0 0 1 0. So first term will be c2, then second term will be minus s2, third term will be 0, then second row, first term will be 0, second term will be 0 0 0, third term again minus 1, and third row C2 S2, then 0 C2 0 and 0 0 0 0. Okay, so I think this I would explain once again. First I just wrote it. So what we are doing is basically there are two rotations here. In the first case it was just a rotation about the z-axis by theta 1, so we directly wrote the rotation matrix which we are familiar, cos theta 1 minus sin theta 1 sin theta 1 cos theta 1 about z, right? Now in the second case, from transforming from 1 to 2, we have one rotation of about x1 about 90 degree, and then a rotation about of theta 2 about the new z axis, right? So that's what we did. So we first rotate about 90 degrees about x, then rotate about z of about by theta 2. Okay, so we have to multiply both the rotation matrix to get the effective rotation. So this is r net. So r net is this multiplied to this successive rotations. So this is how we deal with successive rotations. Okay, and again individually it's easy to write these matrices. Rotation of 90 about x-axis, so the x part will be 1. Here is cos theta is 90, so 0, so minus sin theta minus 1, and so on. And then about z theta 2, this is same, and then we multiply it, so we get the final rotation matrix, right? So let's fill it in here. C2 minus S2 0 0 0 minus 1 S2 C2 0. So this is transformation from 2 to 1, and then finally from 3 to 2. Okay, so 3 to 2 is again straightforward. There is only single rotation involved about theta 3, and there is a translation by L2, so which you can write very easily. Displacement by L2 and rotation cos theta 3 minus sin theta 3 0 sin theta 3 cos theta 3 0 1 0. Okay, so we have all the three transformation matrices, homogeneous transform matrices, and this we wrote without using any formula from our memory. We just wrote it using the basic concepts of rotations and translations. So for simple systems, I would suggest you should write like this only, because this will help you much more than just remembering a formula and putting values in them. So finally what we need is from 3 to 0, which is from 3 to 2 multiplied with 2 to 1 multiplied with 1 to 0. Okay, so basically you multiply all those to get the final transformation from the third frame to the base frame, and that's what we had. So base to world. Okay,
Sir,
yeah.
can you just scroll a little up, sir? The RNet one. Okay,
RNet.
sir. Here first we rotated about x-axis, no, sir. The frame one, and later we have rotated it along z, no, sir. That z is individual axis rotation, sir, without affecting x1 frame. I mean,
Yeah.
without affecting x1 axis and y1 axis.
Yes.
We
So basically, what we did is that. So what we are doing is we are trying to find a transformation. So we are trying to find a rotation matrix which will rotate us from. So this is a rotation matrix from 2 to 1. This notation is like that only, right? transformation from 2 to 1. Okay, so this transformation matrix, if multiplied by a point in frame 2, will give you the point's description in frame 1, right? Agreed?
Yes, sir.
Okay, so yeah, is there any doubt in this part?
So geometrically, can you tell, sir?
I'm coming on to that, but this point is
Okay,
clear that this, what's the purpose this transformation matrix is achieving? It's transforming from a point which is described in frame 2, which is at this joint, to frame 1. Okay.
yes, sir.
Now geometrically what's happening? So geometrically, to basically make frame 1 coincident with frame 2, what are you doing? You are first rotating it about x1, right, by 90 degrees. So let me
Yes, sir.
draw them separately. So let's say in any arbitrary position of the manipulator, let's say these are the frame positions. This is z1, this is x1, and this is x2, and z2 is out of the plane. So let me draw it like this, z2, right? So what do? We first rotate around x1 by plus 90 degrees. Okay, so what do we get? We will get x1 will be as it is because we rotated about it, and then our z1 will be here. So this is an intermediate frame. Let's say we mark it x1 dash and z1 dash, right? This is an intermediate frame. Okay.
Sir, it won't coincide with the x, sir. X1 dash.
Yeah, it will coincide with x. This is because the first rotation I am just rotating it. So there I will do the other steps of transformation also. So first step is just rotating about x1.
Okay.
Okay, bringing z1 out of the plane by 90 degrees.
Okay.
So now our z1 dash is parallel to z2. Okay, because z2 is also out of the plane, normal to the plane, and by rotating about x1 90 degrees, we have also made z1 out of the plane, and x1 dash and x1 are still the same. We have not done any translations yet. We have not done any rotation about z2 or z1 dash yet. Okay, so first step is this rotation by around x1 by 90 degrees. So this is the resulting what the frame will look like, the intermediate frame. This is not the final product, this is the intermediate product. Now after that, what we do is rotate. Now since z1 dash and z2 dash, they are effectively the same, just they are parallel, right? But direction of each of them is the same, right? So what you can do is you can rotate, you can either write z1 dash, or for just uh, since we have final frame z as z2, I can write rotate about z2 axis by theta 2 angle. Fine. So what will the new frame will be? Now this thing, so you can draw the new one, the new frame, which is okay. I should not write z2 here yet, because I will only write them when they become coincident. They are still not coincident, they are just parallel in this case. I will write this is parallel to z2 currently. So okay, so let's also write here z1 dash. So z1 dash and z2 dash are parallel, and rotation matrices writing about parallel axis is effectively the same. So z1 dash, about z1 dash, we rotate by theta 2. Okay, so what will happen is that initially our x1 dash was here, now it has rotated by theta 2 angle. Okay, and now it is parallel to x2. this okay, write it as x1 double dash. Now this is parallel to x2. Any doubt still here? Hello. Okay, so right, so now what we have is that we have z1 dash parallel to z2, and we have x1 double dash parallel to x2. So effectively we have aligned these two direction wise. Now to make them coincident, what's the third thing which is missing? Right, which is the translation part. Right, translation by this L1, right, along the initial x1 direction. Right, so basically you take the origin and move it by L2. So finally move it by sorry, L1, and finally it becomes the rotated thing which we want to achieve, this x2 and this. Okay, I have drawn it like this, so this z2, right? So finally we achieved that. So three things: first, rotation 90 degree about the x1 axis, rotation about theta 2 by the about the z2 axis, which is parallel to this z1 dash, and finally translation by L1 about the x1 along the x1. So basically, if you would remember, how did we get the formula of the transformation matrix? These four quantities correspond to translations and rotations about z and x axis, right, which we had mentioned in the when we discussed dh parameters, that this is a rotation about the z, this is a translation about z, this is this is translation about x, this is rotation about x, and we effectively multiply all of them to get this translation matrix, and which is what I did here, right? So that is how we get the R net. So R net will R net goes in here and corresponds to the rotation part. So what is the rotation transformation from 2 to 1, and this part takes care of the translation transformation from 2 to 1, right? So that's how we make up this transformation matrix. Is it clear now?
Yes, sir. It is clear.
Okay.
Yes, sir.
Okay. Okay, so that was this question, writing the DH parameters and writing the transformation matrices. So let's discuss one more question. We have enough time for this, I believe. So let me zoom it in. So I'll give you a minute to read this, and then I will explain. So what we have to do here is to sketch the workspace, the reachable workspace. We have done it for 2-hour manipulator earlier also. This is also 2-hour manipulator, but there we did not consider one thing, is the joint limits. So what if there are limits to the values which theta 1 and theta 2 can take, and these cases arise again frequently in practical implementations of manipulators, because not every manipulator rotates 360 degree at every joint, right? There is a limit, there is a mechanical limit also, that how much a link can move, and that is done in order to ensure safety, ensure that it does not collide with other links. So that's the case here. It's given that theta 1 has a limit from 0 to 180 degree, and theta 2 has a limit from minus 90 to 180 degree. Okay, so first uh, let's visualize these limits, right? So this is the base frame, right? So theta 1 can go from 0 degree, which is here, 0 degree is here, to 180 degrees, which is here, right? So it can go from directly along plus x0 to directly along minus x0, this first link, right? Now the second link can be from, so this is the direction x1. So with respect to x1, the limits are minus 90 to 180. So minus 90 will be here. This is minus 90, right? So from minus 90 to 180. So it has a range of 270 degrees from minus 90 to 180, which is here, right? So let's say in this configuration itself, which is shown in the figure, if what are the extremes of the second link, it can be like this, right, in which theta 2 is minus 90, right, and it can be fully folded on top of it, right? So in this case theta 2 is 180 degrees, right? So for any theta 1, for any theta 1, these are the two extremes of the second link, right? So how do we draw the workspace? So workspace is what we need to find the, to sketch the area we need to find the boundaries of the workspace. And as you would think, boundaries are achieved when either of the joints are at their limits, right? So because those are the edge cases, when either theta 1 or theta 2 or both of them are there at their limits, right? So now this figure might look seem that how did it arrive, but let's break it down and do it part by part. Let's build this workspace part by part. So just follow along with me and try to, it will take some imagination also, because we are moving two links in the space. So first let's start from this, again, is the image clearly visible to all of you, this image?
Yes, sir.
Yeah. So this since I drawing it with hand might not be as clear as this, so I took it directly from the book, but I would explain how did we arrive on this. So let's draw the axis. This is the positive x0 and this is the negative, right? So theta 1 can go from here to here, right? And as they would see, if let's say if there would have been just one link, this first link, this first link, and let's mark it a second link, so it would move in a circular path like this, right? Circular path like this. And imagine when theta 2 gets folded on this, right? So this thing is similar to what we discussed, like when the second link is folded, there is the inner boundary that you get. So I would use a lot of colors here to mark different parts. So first let's start from the easiest one. Let's talk about this edge, this boundary. Oh. This green one. So C1. Let me mark it as C1. So C1, when do we get? When theta 1 is anything arbitrary and theta 2 is 180 degree, right? Because theta 2 is 180, then only the link 2 is folded on top of it. So theta 2 is 180 and theta 1 ranges from 0 to 180, right? That's the limit of theta 1. So when the first link is completely lying down here and link 2 is folded on top of it, so that is this point, and again first link is lying down here and then completely folded on top of it, right? So this corresponds to the green part. That's the easiest one. And the second most easiest one is the very outermost one. Again, these two are the ones which we have seen in our drawings of the 2R manipulator workspace. So this outer part till here, no, till 180 degrees, till here. So this is which case in which theta 1 is arbitrary and theta 2 is fixed at 0, the full extension case, right? So C2 is theta 2 0 degree and theta 1 varies from 0 to 180, right? So that is, so two edges which you would also have guessed how are they being generated, that we did. Now let's go on to the interesting parts, the parts which are slightly involved. So first let's look at this feature on the left hand side, this one, right? This violet one which I am drawing, C3. So imagine how would this edge be created. In fact, this would be created when the first link would be at fixed at, it would stay at this 180 degrees, right? Now when link 1 is at 180 degree, then its plus x, positive x axis is x1 axis is here, right? And then from 0 to 180 theta 2 can go, right? Minus 90 will lie just inside here, which is taken already taken care of in this space. What new space are we getting is that when link 2 will move from 0 to 180 here, right? So then we'll get this area, this additional area. So this C3 we get when theta 1 is 180 degree and theta 2 varies from 0 to 180 degree, which is inside its range because its range is minus 90 to 180. Any doubt still here? Okay, so we have sketched uh, most of the parts of the workspace. Now let's come to the right hand part. So right hand part, you see a very unique kind of feature in which we see two distinct curves here. In fact, three curves are there. So let me first mark them. So one curve is this, which I am marking with this sky blue color. This is, let's say, C4. Then another curve I am marking now with this black color. This is C5. And finally this C6. Okay, so let's figure out what are the values of theta 1 and theta 2 for which we achieve these edges of the workspace. Okay, so here I would need your imagination to be firing. So, and my sketching skills would also be helpful to you. So let me draw some sketches. So now focus entirely on the right hand side. So first scenario can be that the first link is flat, theta 1 is 0. So first link is flat. When first link will be flat, as I drew this dotted line, it would come somewhere till here, right? The first link when it's flat. Okay, it's getting slightly dirty, but just bear on with me. So this red dotted line is what will be the position of the first link when it's entirely flat, theta 1 is 0. Now in this position, what all things theta 2 can do? Okay, so first what it can do is basically it will move to, let's say, the wait, theta 1. So first, let's say when theta 1 is here and theta 2 is fully folded, right? So the end effector will be at the start of this blue zone, okay? And this blue zone, and then as theta 2 goes from decreases from 180, we will move on this path, right? On this path we will move, and the end effector would come back to the other region, the already marked region, right? So that's how we will get the blue space, the C4 line. And similarly, when theta 1, right, when theta 2 is, so let me first mark the C4 one. So C4 is, did you get the C4 one?
Yes, sir.
Okay, thanks for the confirmation. So C4 है when theta 1 is 0 and theta 2 varies from 180 to some theta. I cannot say entirely which. I think it will be, yeah, it will be some theta. Now the other thing which you can see is that when when theta link is lying here and theta 2 is minus 90, so the end effector will be here, right? And then from that place the end effector will start moving, okay? So it will move in this kind of a path, right? So from minus 90 to 0, and then from here it on it will move inside again, so again it will come to the already covered workspace, right? So this c6 we get when theta 1 is 0 and theta 2 is, I think here I made a mistake, it should be less than. So here theta 2 decreases from 180 to some value. That value I can't tell. So here it decreases from minus 90, theta 2 goes to 0, and then it goes inside the same already discovered workspace, right? So C6 C4 are done. Now how do we get C5? So let's think about that, because link 1 can't go below this, right? Because link 1 is limited at 0. So link 1 is here. Now what will happen is that, imagine link 2 is at its limit, right? Link 2 is at its limit, and then we are moving link 1, right? So this is basically an L like shape, you know an L like shape, and you are moving its end. You can move like this, it will go like this. The fixed L shape is moving in counterclockwise direction, and that path will trace this one, and at this till this point, and then move on to here. It will go inside the workspace, so it will intersect this curve here. So that case is when theta 2 is fixed at minus 90 theta 2 is fixed at minus 90, and theta 1 increases from 0 to some angle, right? So that traces the C5. Oh, I mentioned wrong. So C6, C4, this is C5, right? So this is an interesting problem. I think it might not be entirely clear, or I might not have made it entirely clear in this description, but I would strongly recommend that you should take a pen and paper and try to figure out on your own. It will be a good exercise, especially the right hand part. The left hand part and the top part is quite straightforward, but the right hand part is very interesting. So you should uh, definitely attempt it on your own also. So yeah, I think we are on time. And so just to summarize, we discussed about the Jacobians today. We saw how Jacobians relate the velocities in the joint space to velocities in the task space, and the transformation between these two. We derived the Jacobian for the 2R manipulator. We saw what are the singularity points for 2R manipulator. Where does the 2R manipulator has uh, highest energy uh, advantage. And finally we solved a few questions based on DH parameter and workspace analysis. So yeah, I mean that's it from my side. If there are any questions you can ask, else we can wrap up for today.
Sir,
Hmm.
you have for this C5 for the C5, sir,
Hmm.
that you told that L shape it moves up,
Hmm.
and like as it moves up, upper and upper, that shape curve is formed, no, sir.
Hmm.
So at that time, theta 2 value also should slightly change, no, sir, or it will remain the same.
I
To get
believe this trace would be carried when theta 2 will be fixed at minus 90. It will be at its limit. Because
okay,
if theta 2 also starts changing, then you would imagine this curve will tend to move more towards the right hand side, and this is much more, you know curvature is much more less. So again, that's why it said, like, to satisfy yourself, no, you should draw this and draw this on your own to just
okay,
satisfy yourself. That would be, it would be much more useful to you than me explaining and convincing you that it is like this. So
okay.
just attempt it on your own.
Yes,
Okay.
sir. So
So
one more thing.
yeah.
The green color one, sir, C1, sir.
Hmm.
There are flat ends, no, sir.
Hmm.
That is just linked to resting on link one, sir.
Yeah, that is linked to resting on link 1.
Okay, okay. So one more I have sent on your YouTube channel. Week two, I posted one comment, sir.
Hmm.
Like whenever you are free, can you just respond to
Okay,
that, sir?
sure, sure, sure.
Uh, on your YouTube channel.
Okay, okay,
Week
sure.
two lectures, sir. I mean, week one and week two are covered in the same
Hmm.
video, no, sir.
Same one.
Under that, I had one doubt. That is
Okay,
regarding a problem.
okay, okay.
Okay.
I will answer
Whenever
that.
you're free, sir.
Okay,
Yeah, that's it, sir.
okay. Then I will hang up for today, and we will meet. Yeah, we will meet next week, same time. Okay,
Thank you, sir.
okay. Thank you, guys.